Welcome to this number theory primer. In this lecture, we'll look at an alternate proof of Euclid's theorem, much like what we did as an alternate proof for the division with remainder theorem. So let us recall the relevant facts. What did Euclid's theorem say? It said that if we have any two integers, not both 0, so that their GCD exists, then one can find integers x and y such that one can write the GCD of a and b as the integer linear combination, the corresponding integer linear combination of a and b. It's a very nice theorem. And let us recall the main key fact that we will need to prove Euclid's theorem in this alternate way is that is the following. If suppose we have two integers a and b, again not both 0, I haven't written that, and suppose a is equal to bq plus r for some q and r in z, meaning some integers q and r, and we are not demanding that r be in some, in this range or something, any such thing, r and q are just some integers, then GCD of a and b is equal to GCD of b and r. Actually, what turns out is that they share all the common divisors, and therefore this is a trivial, or rather, is an easy fact. We proved it earlier. Lastly, I would like to recall a version of the well-ordering principle. So suppose I have a set S, and of course I'm assuming it's non-empty, and we are given some function, any function from S to n. Then there is some element of S for which this inequality is satisfied, meaning it is the smallest, or rather I should say, the f value at that point is the smallest amongst all f values. So that's what this is. And this is nothing more interesting than the standard well-ordering principle, which says that any non-empty subset of natural numbers has the smallest element. It's an immediate corollary of that. But this is the form that we will use. All right, so let's get started. So Euclid's theorem is applicable to any two integers, not both of which are 0, but I will give the proof only when a and b are natural numbers and let you figure out the two cases where b could be negative, a could be negative, and so on. So we'll assume a and b are natural numbers, and then we want to prove that one can find integers x and y such that the correspondingly integer linear combination, or just this quantity, is equal to the GCD of a and b. So all right, what we will do is we will collect all the bad things. So S be the set of all those pairs of natural numbers for which one cannot find integers x and y. So there do not exist integers x and y satisfying ax plus by equals GCD a and b. So collect all such pairs, and the problem, or the Euclid's theorem, is as good as saying that S is an empty set. So that is our goal. So assume on the contrary, that S is not empty, and define a function as f of a comma b equals a plus b. So just think of f as something that measures the size of things in S. This is one way to measure the size. There could be other ways which work equally well, but this is the most convenient. So f is the size function, you can think of it that way. And now, since S is assumed to be non-empty, we can find an element in S such that the f value at that particular element is the smallest possible f value over all elements of S. So this is what we called the version of well-ordering principle that we are going to use. It's a trivial statement. So there is such a thing, and now we have three cases. So case 1 is a naught is equal to b naught, case 2 is a naught is greater than b naught, and case 3 is a naught is less than b naught. Right? A naught and b naught are two natural numbers, so one of these three cases have to hold, and we will eliminate all the three cases and hence come to a contradiction, which will prove the fact that S is actually empty, and we will be done. So first, we'll assume that a naught is equal to b naught. So let's dispatch this quickly. Then GCD a naught comma b naught is what? This is equal to a naught, and a naught is also equal to a naught 1 plus b naught 0. And therefore, a comma b is not in S, which is a contradiction because a naught comma b naught is not in S, which is a contradiction because a naught comma b naught was a member of S. Right? A naught comma b naught was the smallest kind of member of S. I shouldn't say the smallest because there could be multiple such things, but we have just fixed one such element in S for which the size is smallest possible. All right. So I hope this reasoning was clear that if a naught is equal to b naught, then we can indeed write the GCD of a naught and b naught as an integer linear combination, and hence that would be a contradiction to the fact that this guy belongs to S, and this case is settled. Now for the second case where a naught is greater than b naught, this is slightly more interesting. So if a naught is greater than b naught, then a naught minus b naught, comma b naught, is at the very least a member of n cross n, right? Because since a naught is greater than b naught, this is a positive thing. All right. Also, the size of this guy, or rather I should say, and the size of this particular pair is equal to a naught minus b naught plus b naught, which is equal to a naught, which is strictly less than a naught plus b naught because b naught is a natural number, which is equal to f of a naught plus b naught. So the size of this pair is smaller than the size of the pair a naught b naught, and hence, therefore, this thing a naught minus b naught comma b naught does not lie in S, because if it lied in S, its size would be smaller than the smallest possible size, and that would be a contradiction. So this implication is there. At the same time, yeah. So since this is not in S, its GCD can indeed be written as an integer linear combination of the two numbers a naught minus b naught and b naught for some x and y, for some integers x and y. But I would like to say that GCD of a naught comma b naught is same as the GCD of a naught and b naught, a naught and b naught. So this I will justify this, but I hope you see that immediately anyway. The right hand side, if we manipulate it, we will get a naught x plus b naught y minus x, and therefore a naught comma b naught, or rather I would say that the GCD of a naught comma b naught is indeed expressible as an integer linear combination of a naught and b naught, and that would mean that a naught comma b naught lies away from S, meaning it is not in S, and that would be a contradiction. So once we justify this equality, we get a contradiction, and hence this case is also not possible. So this equality happens simply because a naught is equal to b naught times 1 plus a naught, one second, plus a naught minus b naught, right? And you can think of this as a naught is equal to b naught q plus r. You can think of it that way. So therefore, we get, by what we recall, that GCD of a naught comma b naught is equal to GCD of b naught comma a naught minus b naught, right? That's what we recalled. But this number is same as that number, just the entries are shuffled, and shuffling entries doesn't change the GCD. So that justifies this equality, and therefore this case is also dealt with. This is also not possible, and case 3 is similar to case 2. So that I leave for you to fill. And therefore none of these cases are possible, and that's a contradiction because at least one of these three cases must hold. So we come to the conclusion that this assumption that S is non-empty must be false, therefore S is empty, and hence Euclid's theorem has been proven. For a and b natural numbers, you can extend this proof to negative integers, including negative integers also. All right, so that's all. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.